Hello analysis. In this video we are going to look at our first of many new integration techniques, the integration by parts technique. Before we do this, I'm going to briefly say a thing about our integration technique unit that we are entering and why we do it. I mean, it's integration. Why don't we just tell a computer to do integration? Or I have some reasons why. This unit is important and should be looked at as an opportunity and a fun puzzle unit in a way. Then we'll review some basic techniques. I'll just briefly remind you the things that you have previously learned. We won't look into them in detail, but I'll just kind of say out loud what you should already know. And then maybe if one of the things that I say, if it confuses you, you can just go back and look at it in the textbook. I have the textbook there at the bottom. All right, and then examples. We're going to do a bunch of examples in this video and how to use integration by parts. The basic rules that you should already know, chapter 8.1, just go ahead and review them. In that chapter, there's a nice little list that just tells you these are the things that have been addressed already in the textbook. And you should have those down solid. The 8.2 is integration by parts. At the end of this video, I'm going to give you an integral that is very difficult. And it's up to you if you want to solve it or not. I'm not going to solve it here. I'll talk to Mr. Schwartz and see if we want to do it in class. All right, but with that said, this is our plan in this video. Let's go ahead and talk about integration. So why the heck do we integrate? Why spend this entire unit learning integration techniques? Why integrate? All right. Reason number one, it makes you smart. All right. Reason number two, it staves off Alzheimer's. And reason number three, it's fun. All right, this unit is kind of silly. All right, we're just going to spend a bunch of time learning how to take the integrals of things that, to be honest, a computer could do for us. Right? But it's really important to know, first of all, how is the computer programmed to do that integral? Right? Are we getting an exact answer, or are we getting an approximated answer because the integral is impossible? But also, we want to train our brain to think critically. And if you are the type of person that loves puzzles, this unit is going to be, I think, a great time. All right. So I lean in and try to enjoy the really cool integrals that you're going to do, because substitution and just basic integration patterns that you've memorized, like the arc functions, are not really entertaining. But this unit, I think that you guys will find value in. I think it's going to be a fun unit. Hence number three. All right, let's begin. In this unit, we are going to develop a lot of integration techniques. And it starts with what you already know. You already know a ton of tools, including, all right, substitution, the power rule. All right, just to write this one down, the antiderivative of 1 over x. All right, that is the absolute value, the natural log of the absolute value of x, of course, plus c. You've been introduced to the antiderivative of e to the x, or the wonders, the beauty of the exponential function. With that said, you should also know that the antiderivative of a to the x, where a is any number, dx, is equal to 1 over ln a times a to the x, of course, plus c. You should also have down all of your trig integrals. All right, there's a lot of them. All right, I'm talking about what's the antiderivative of sine x, cosine x, tan x, like all of their reciprocals. But also, you should know the antiderivative of cosecant squared x, secant squared x, secant tan, and cosecant cotan. I'm running out of room there. And last but not least, you should know the derivatives, and thus you should know the antiderivatives of, you should know the derivatives of the arc functions. Arc sine, arc cosine, etc. You know a lot of integration techniques already, but a lot of this is just you know what to do. We are going to be looking at a ton of approaches to integrals that you have never been able to do before. You know what, while I'm at it, let me not just say etc. because I do want you to know which ones you need to know. We have arc cosine, arc sine, and then also arc tangent, arc cotangent, arc secant, and arc cosecant. All right? And I'm not asking you to find the antiderivatives of these. I'm saying you know the derivatives of all of these. So you need to be able to work backwards. All right? For example, arc sine x is 1 over the square root of 1 minus x squared. So if you see this object, if you see this expression, you know to work backwards to get the antiderivative of 1 over square root of 1 minus x squared. That's arc sine x plus c. Let's do a problem from the past. Let's do a problem that you could ideally already do, right, to activate our brain, and then we will get into our first of many new integration techniques. We are going to be looking at integration by parts today. All right, so like every integral that I do later in this video, I highly encourage you, because the only way you're going to get good at integrals is to fail and fail and fail and fail and fail 1,000 times, and then with practice, you will start to notice patterns and you will be successful. So I highly suggest that you try to tackle the integral that I'm about to write before I do it. You currently have the prior knowledge to do this. I believe in you, and I'm sure Mr. Schwartz does too. The integral of 1 over a squared plus x squared dx. A is a constant. X is our variable of integration. All right, I'm going to begin this problem in 3, 2, 1. All right, hopefully you were successful. If not, all right, this looks very similar to the integral of 1 over 1 plus u squared, which is something that you should just know. To be frank, this is arctan u plus c. Whoop, whoop. Arctan u plus c. But this a squared is messing things up. So what do we do? Let's use u substitution to turn this thing in to this thing over here. All right, I'm going to factor out an a squared, or sorry, a 1 over a squared. Factor out a 1 over a squared. That is going to be 1 over a squared times 1, beautiful, plus x squared over a squared dx. From here, I'm going to take that 1 over a squared out, and then I'm going to make this look like my antiderivative of 1 over 1 plus u squared. I'm going to write this as 1 plus x over a quantity squared dx. And then I'm going to set u equal to, and actually let me not use u because I'm using that in the upper right hand corner right now. Let me call it w. I'm going to call w x over a. And this is, in this case, w substitution, but I'm going to, or w substitution, but I'm going to take the derivative of w, and I'm going to get, with respect to x, sorry, and I'm going to get 1 over a dx. And this becomes a u substitution problem, becomes an arctan problem, and we'll be done. Let's take it to the next page. And let's rewrite. All right, this is going to be 1 over a squared. All right, I'm going to replace, I'm going to do a little bit of extra algebra here. A dw is equal to dx. I'm going to replace dx with a dw. Arthur reference, love it. 1 plus w squared. All right, one of these a's and this a are going to cancel. I'm going to have 1 over a, 1 over 1 plus w squared with respect to w. All right, and then boom, I believe it's as simple as that. All right, this is going to be 1 over a times the arc tan of w plus c. But wait, there's more. I didn't want the antiderivative of this with respect to w. I wanted it with a u in it. Or sorry, not u, x. My bad. I want it with an x. So let's go ahead and finalize this problem by substituting x over a back in. So the final answer here is 1 over a times the arc tan of x over a plus c. All right, don't forget that plus c. So, with that said, right, if you want to take the antiderivative of 1 over a squared plus x squared dx, we now have a formula, or you could just redo that process. And that's kind of the goal in this unit, is no matter what you're given, you can always rederive and relearn the integral rule based on the rules that we're establishing. All right, so this is going to be 1 over the square root of a times the arc tan of x over a plus c. Ooh, sorry, that a needs to be square rooted. There we go. Boom. So you can use that. And then if I want to take the integral of 5 plus x squared, that's just going to be 1 over the square root of 5 arctan of x over the square root of 5 plus c. Right? So we are establishing rules using what we already know. All right? And integration by parts, which we will look at on the next page, is no different. Right? It's going to be rooted in what we already know. All right, so let's look at integration by parts, which I will sometimes refer to as IBP. All right, let's motivate this thing. All right, integration by parts is going to be some sort of formula. Right? Let's say that I have the antiderivative of x sine x dx, and you're like, woo, so easy. I got this. Let's just like do a u sub. Let's like, uh-oh. I can't do u step. U sub. I can't do u sub. Step 1 in all integral problems. Try to figure out if there is an easy way to do it. And it would be great if we could have used u sub. Does u sub work? Here it does not. And I'll let you guys try to use u sub if you want. But u substitution is not going to work here. Right? Is this a pattern that we recognize? No. Right? We need a new way to take the integral of this. And what we already know is not going to work. If this was the integral of x sine x squared dx, we'd be in business. We could set u equal to x squared. Right? Du is equal to 2x dx. And then just boom, it becomes the antiderivative of believe sine u. Right? Because it's going to be sine u. Oh, there's going to be a 1/2 there, but regardless, right? That would have been great. Right? Before you do integration by parts, or you do any of the integral techniques that Mr. Schwartz and I are going to be teaching you over the next few weeks, try to do it the easiest possible way, which in general is going to be u sub or some pattern that you've recognized, like the arctan function that we just did. This is happy. This is sad. So what the heck is integration by parts? Well, integration by parts is a technique that we use when there are multiple functions under our integrand. For example, the one we just looked at. Right? We have the function x and the function sine x. Right? Integration by parts. There are multiple parts to this integral. And as we know, we can't break this up into this, right? Because of the chain rule. All right, pause. I just said the chain rule when I meant to say the product rule. And I'm about to say it a bunch more. So just to clarify, I meant to say the product rule. So you may proceed. All right? If I have f of x times g of x, and I take the derivative of this thing, I'm not going to get f prime of x, g prime of x. I'm going to get f of x times g prime of x plus f prime of x, g of x, right? The chain rule, right? Let me just move this over real quick. Cool. X, right? Let's take the antiderivative of both sides of this equation. All right, and then we're going to get, what is it going to be? We're going to get f of x, g of x, and then over here we're going to get f of x, g prime x plus, right? I can break this up, right? The sum of integrals is the integral of the sum. If we do some fancy moving around, I'm going to move this to the other side of the equation. We're going to get something that is quite convenient. All right, I'm going to get f of x, g prime of x dx is equal to f of x times g of x minus the antiderivative of f prime of x, g of x dx. There should have been some, when I took the antiderivative, I should have done it with respect to dx every single time. Let me go ahead and add that. Right, boom, this is our integration by parts formula. And you're looking at this, you're like, what the heck does that even mean? Right? Let's make sense of this. Compare it to my example up here. Right? If I want to take the antiderivative of a function times another function, if I integrate, or if I integrate one of these functions to get f of x, g of x, and I take the derivative of one of these functions to get f prime of x, g of x, I might be able to simplify this thing. Like, think about it. If I call f of x, x, and I call sine of x the antiderivative, if I call g prime of x sine of x, then over here I'm going to get x, I'm going to get negative cosine x, that's pretty straightforward, minus 1 times g of x, which we just called negative cosine x. Right? I couldn't take the antiderivative of x sine x, but I can sure as heck take the antiderivative of negative cosine x, right? And then I'm in business, I'm done, right? Because that's all I needed to do. This is what I wanted, and this is all I have to do, right? We are exploiting the chain rule so that we can take the antiderivative of the product of functions, right? Integration by parts. We are looking at two parts of a product, and we are going to turn it into something that we can take the integral of using prior skills, like use substitution, or just knowing that the antiderivative of negative cosine is negative sine plus c, etc. You will often see this formula. Let me put it in a new color. You will often see this formula written with u's and v's. No real reason, just it tends to look nice, and it's common. All right, u dv is equal to u times v minus v du. All right, this is the same thing I had on the previous page. A function times the derivative of some function is equal to the first function times the second function minus the antiderivative of the integral of that second function times the derivative of the first function. All right, u dv is equal to uv minus v du, the antiderivative of v du. All right, try out this integral, x sine x dx. All right, my suggestion to you is to, when you do this technique, integration by parts, develop a routine so that you do it the same way every single time. And my suggestion is to write your u function, write your dv function, write your du function, write your v function. All right, we're given dv, we're given these two things, right? X sine x. Right? Take the antiderivative, 1 dx. Take the antiderivative. I'm not sure if I said antiderivative or derivative here. Take the derivative, take the antiderivative over here, negative cosine x. And then this, the integral of x sine x dx, is going to be u times v. Let me change up my colors. I suggest writing it in this direction every single time. U times v. So that's x times negative cosine x minus, right, v du. All right, we didn't use dv. Well, we did. We were given dv to find v, and we're using v twice. All right, so x times v, or so u times v, minus the integral of v du. All right, I always do it in this direction. I write it like this, and then all I got to do is translate it. All right, v du. All right, negative cosine x times 1 dx. Boom. And I believe we're home free, right? Negative x cosine x minus minus. I'm going to turn that into a plus plus. And then this becomes plus sine x plus c. Don't forget that. Please don't forget the c. Right? And then we're done. Right? Something that we couldn't take the antiderivative of at the beginning, we can using this exploitation of the chain rule. This page presents an issue, though. Right? How did I know to make u x and dv sine x instead of u being sine x and then dv being x? All right? I encourage you to pause the video and do it the other way and see what happens. But my pro tip to you, right? Pro tip, here's a red flag. This is something that you should pay attention to. This is something that you should write down. Right? Make your dv as complicated as you can make it. Make your dv the most complicated that you can. The most complicated that you can integrate. All right, because there is a hidden option here. You could have said that u is 1 and dv is x sine x. The problem is you can't take the antiderivative of x sine x. Right? So my tip to you is to make your dv the most complicated that you can, in that you still can integrate, though. All right, let's do another example. All right, once again, I highly encourage you to try to do this integral before I do it, because what makes you good at integration, what makes you good at solving puzzles, is solving more puzzles. Right? Practice, practice, practice. You will not get good at this if you just watch someone else do it. Try to do this. X squared e to the 3x dx. All right, step 1. Can you use something that's easier? Can you use u sub? Is there a pattern here that you recognize, like 1 over 1 plus x squared or 1 over 1 minus x squared? Right? Is there a better way? In this case, there isn't. Sad face. All right, I'm going to proceed in 3, 2, 1. What is the most complicated thing I can make my dv? Right, and I'm going to do this. I'm going to write u dv, and then underneath it du and v. All right, I always write it in this grid here, in this order, and then I'm going to go uv v du every single time. I highly suggest using this technique. Right? What is the most complicated thing I can make dv? Well, I mean, there's some options here. Right? X squared, e to 3x, both are fairly simple. Right? I'm in this example going to go with e to the 3x. All right, and I have a reason why, but I want to see if you understand the reason why as we proceed. Right, so I want you to kind of come up with it on your own. U is going to be x squared. All right, du will be 2x dx. V is going to be e to the 3x, and then we're going to have a divided by 3 there, right? All right, now that I have my chart and I've already given you the arrow, I've already given myself the arrow, I'm going to rewrite this integral over here as uv x squared e to the 3x over 3 minus, all right, that's a minus, please don't put a plus, right? Antiderivative of, integral of v du. So 2x over 3 e to the 3x dx. All right, you might be saying to yourself, that is not any more simple. Right? I still have a function times another function. But what did happen? Our x squared term reduced by a power. Right? And that is the essence of why I've chosen u to be x squared, whereas dv is the e to the 3x. Right? I can constantly integrate e to the 3x, and it's never going to simplify. There's always going to be a function there. But if I take the derivative of x squared, I lose a power. And if I do it one more time, I'm going to lose a power again, and I'm going to be able to integrate e to the 3x, whatever that junk is. There's going to be some constants. But if I do this again, I'm going to lose a power again. Right? So think to yourself, why is it smart to make u the thing that's going to disappear, whereas dv the thing that will not necessarily disappear? All right, I'm going to proceed. I'm going to do this one more time. So over here, I'm going to be smart. I'm going to go ahead and take that 2/3 out. All right, I guess you could handle it. I prefer not to. All right, this is going to be x e to the 3x dx. And then I'm going to use integration by parts again. Okay, so my u is going to be the x. My dv is going to be e to the 3x. My du is now 1 dx. Perfect. And my v is e to the 3x over 3 again. All right, and then down here, I'm going to have x squared, e to the 3x over 3, minus 2/3 times, here we go, x times u times v, is going to be x e to the 3x over 3, minus, all right, the minuses are going to become something that is cumbersome. All right, be careful. I encourage you to just carry those minuses down and deal with them later. All right, the integral of v du, so that's going to be e to the 3x over 3 times 1 dx. We have now gotten rid of the product. We can just take the antiderivative. All right, no more product rule necessary to worry about. Let me go ahead and grab this, take it to the next page. So that we can finish up this problem. Okay. We have x squared e to the 3x divided by 3 minus 2/3 times, and you know what, while I'm at it, I'm just going to write 2/3 x e to the 3x divided by 3. That's going to become a 9. And then I have the plus, because this negative is being distributed over here, plus the antiderivative of that, which is e to the 3x over 9 plus c. Oops, I did exactly what I told you guys not to do. I'm being very careless. This 2/3 is also hitting this 9. So I believe, I'm going to, one last line. I'll write this as fast as I can. Plus 2e to the 3x over 27 plus c. All right, so what did we see here? We made the most complicated thing that we could, dv. Right, but in doing that, we had to do integration by parts twice. Because by doing it just once, we have downgraded the power of u to a linear function, but we needed to do it one more time so we get something without any variables so that we can easily take the antiderivative. Right? Integration by parts is sometimes a repetitive process. All right, let's proceed. Here's another integral, right? X times sine x squared dx. All right. I'm going to do this problem in 3, 2, 1. All right, can I use substitution or some other technique? And guess what? This is a trick. I absolutely can. I'm going to set u equal to x squared. I'm going to set du equal to 2x dx. This is the problem that I put at the beginning. All right, if you didn't notice that right away. All right, and this becomes, let's see, becomes sine u and then 1/2 du, right? Because du is 2x dx, so I have I need a 2x dx. Yep, that is right. 1/2 sine u du. This is going to become 1/2 negative cosine u plus c, and then u is x squared. So this becomes 1/2 negative cosine x squared. And a quick check will verify that this is correct. Plus c. Don't forget that. I almost did. All right, that was a 30-second problem just to troll you. Here is one that may, or may not, require integration by parts. All right, x cubed cosine x squared. All right, I encourage you to do this one before I attempt it, because I cannot drive home the point enough that practicing integrals and getting used to these techniques is the best way to notice them when you're given an arbitrary problem. All right, right now I'm giving you a bunch of integration by parts. All right, in a week or two, Mr. Schwartz and I will be giving you just a sheet of who knows what, and your job is to be able to identify if integration by parts is necessary. All right, so look at this and think about why this is an integration by parts problem. Right? Is there a u that will deteriorate and disappear? Is there a dv that's easy to take the integral of? And with that said, I'm going to do this problem in just a second, so pause the video and solve it. Here I go. 3, 2, 1. All right, you might think that the dv here should be cosine x squared, but you can't take the antiderivative of cosine x squared. Right, because when you work with this, you need a x there, right? Because we're going to do this with u substitution. So the key here is to recognize that dv is actually x cosine x squared. U is going to be x squared. du is 2x dx. V ends up being, think about taking the antiderivative of this. That's going to be 1/2 sine x squared. All right, we got some chain rule action here. The 2 comes down. Going to cancel out with that 2. The x pops out, and we're going to get cosine x squared times x. Excellent. So this is our u dv, our du, and our v. I need these 3 things to proceed. This is going to be x squared times 1/2 sine of x squared minus v times du. And actually, this is going to be really good for us because the 2's are going to cancel. Awesome. And we're going to be left with an x sine x squared dx, which we just did on the previous page. Our final answer is x squared sine x squared of sine x squared divided by 2. And then it's going to be minus a negative 1/2 cosine x squared. So a plus 1/2 cosine of x squared. And of course, plus c. One of the trickiest parts about doing an integration by parts problem is establishing what the u and the dv are. All right? Think about what the most complicated thing you can take the integral of. All right? We cannot take the integral of cosine x squared. We needed an x. Right? And this is mildly complicated. Much more complicated than x cubed. Right? That's the pro tip. Try to set dv as the most complicated thing you could take the antiderivative of. All right, new problem. What is the antiderivative of arctan x? Why the heck would I put an arctan function on a integration by parts video? Right? Didn't I say it's by parts? Parts meaning there's the product of 2 functions? Or are there really 2 functions here? The function 1. All right, let's set u equal to arctan x. We know how to take the antiderivative of that. That's just 1 over x squared plus 1. We did that earlier. All right, dv, let's set that to just be dx. That is the most complicated thing in this product that we can take the antiderivative of. That's just x. And then boom. Right, uv, so we have x arctan x minus the antiderivative of x times O my gosh. Can you take the antiderivative of this? I bet you can. I see a couple ways to do it. All right, but I think the best way is use substitution. Let's let x squared be u, and then du be 2x. Divide by 2, we got 1 over 2. Du is equal to x. Boom. Oops, sorry, there should be a dx right there, a dx right there. Replace that x dx with 1/2 du. And we have ourselves, I'm actually going to pull that 2 out, 1/2, and then I'm going to put that, I don't know why I wrote it that way. I'm going to put the du there, put a 1 there, and then we have a u plus 1. All right, what is this? That's the natural log. X arctan x minus 1/2 the natural log of the absolute value of u plus 1 plus c. But let's go ahead and rewrite u as what we just said, x squared. Boom. What an integral, right? Why do we integrate? Because it's interesting, because it's fun, because it's a puzzle, right? Your goal is to become a master of integration by parts before proceeding, so that as we add more and more techniques, you can spot the IBP problems. I got one last problem for you, and it's a doozy. E to the 3x times cosine 2x dx. In just a moment, I'm going to prompt you to try this problem without any help. Right? You will get halfway through this problem and think you're doing something wrong. Right? But that's why you need to be doing math with a pencil, because you are going to need to maybe erase. Right? The best way to get good at these integrals is to try, to fail, and then to try again. And this is a doozy, but if you stick it out and you keep going, I promise you, you'll be satisfied. It's a difficult problem, but you can do it. I'm going to start it in 3, 2, 1. Okay, we have the product of two functions, e to the 3x and cosine 2x. Right, I need to decide to myself which one is going to be my dv. Let me go ahead and fill out my chart. Which one is going to be my dv? I'm going to go ahead and make e to the 3x my dv. But you might be able to argue that cosine 2x could be your dv. That is also going to repeat. Right? Both of these are not going to deteriorate. You can just keep taking the derivatives. And for cosine, it'll cycle through sine and cosine and negative sine and negative cosine. E to the 3x will just repeat itself. Okay? I'm a little bit worried. All right, but let's proceed and let's see if something magical happens, as that happens a lot in math. Right here, we're going to have e to the 3x divided by 3. And over here, we're going to have negative sine 2x times 2. Let me go ahead and make room for that times 2. And you know what? I need to make room for my dx as well. So I'm going to go ahead and do that. Sorry about that email sound. Du is negative 2 sine 2x dx. All right, at this point, it's just a do it problem. Let's continue. All right, uv, that's going to be cosine 2x times e to the 3x, all divided by 3, minus v du. Right, if it helps, you can draw the little arrow, right, diagonal over. The antiderivative of, I'm going to go ahead and take this negative 2 and this 3 and put it here. All right, that's going to be helpful to me. Sine 2x e to the 3x. Uh-oh. That doesn't look much more simple than what I previously had. All right, let's not give up. Let's continue. All right, let's do the same thing again. All right, we have cosine 2x e to the 3x divided by 3 plus 2/3. All right, we gotta be really careful, unlike me earlier, about not dropping anything. Or we're going to do another integration by parts. Let's call u sine 2x. Then du is going to be a positive 2 cosine 2x dx. And let's call dv e to the 3x again. And then v is going to be e to the 3x divided by 3. And then we're going to do a little boom, boom, boom. Sine 2x times e to the 3x all over 3 minus the integral of, once again, the 2 and the 3 I'm just going to pull out. Cosine 2x. Wait a second. This is exactly the same as what I was given at the beginning. Huh. Have I not made any progress? Or have I made so much progress that it's just doable? Right? Am I insane, or am I so smart that something beautiful is about to happen? I'll let you decide. Let me rewrite something. Let me rewrite this is equal to this on the next page. All right. E to the 3x cosine 2x dx. That's equal to cosine 2x e to the 3x divided by 3 plus, let me go back, make sure I got it right, cosine 2x e to the 3x divided by 3 plus 2/3, that's going to be 2/9 times sine 2x e to the 3x. All right, and I hope it's clear that the e to the 3x is not within these functions. All right, and then I have plus, let me go back. All right. Oh, look, it's going to be a minus, actually. Minus 4/9. The integral of e to the 3x cosine 2x dx. Huh. Is this solvable? All right, pause the video, look at the screen, and see if you can think about a way to solve this. You know what? I'm going to give you 10 seconds of awkward silence so that even if you choose not to pause, you still have to look at this for a little bit of time. Do you see that the integral is on both sides of the equation? Right? I want to find out what this thing is. Right? If I gave you the equation, 2 of something I want is equal to, I don't know, 3 plus 7 plus 4/9 of that thing I want, you'd solve for x. Right? You'd move the 4/9 to the other side. I don't know why I use these numbers, and then I did use 4/9, but don't let that distract you. You'd move this over. You'd then multiply whatever by the reciprocal of whatever this number is to isolate x. Right? This is some whoosh, whoosh, swingy action. We are about to swing that integral on the right-hand side over to the left-hand side, multiply by, I believe it's going to be 13/9, or it's going to be 13/9. We'll multiply by 9/13, and we will have our integral. We will be done. This is some swingy whoosh, whoosh, action. Let's solve. All right, let's add that 4/9 of the integral to the other side, and we're going to get 9/9 plus 4/9. That's, as I said a second ago, 13/9 times the integral that we care about. And then over here, we're going to have cosine 2x e to the 3x over 3 plus 2 times sine 2x e to the 3x. Let me throw some parentheses in there. Divided by 9. Multiply by 9/13 on both sides. Bam, 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 bam. Those all cancel out, and we're left with e to the 3x cosine 2x dx, the thing that we wanted. What is the antiderivative of e to the 3x cosine 2x dx? That is going to be 39 9/39 times cosine 2x e to the 3x plus 26. Oh, no, not even 26. 9 times 13. Yuck. That's 90 plus 27, or 117. 18 sine 2x e to the 3x. And then we could simplify this a little bit. We could factor out a e to the 3x. We could factor out a 13. I guess that would just be taking us back here in a way. I don't know why I actually distributed it. Oh well, but we're done. That's the answer. Right? Let's not forget plus c, but that's our answer right there. We are in business. That was some excellent swingy, whoosh, swingy, whoosh, action. And for those who like to torture themselves, I have one last integral that I'm not actually going to do in this video, right? But if you want a challenge, here's an integral that's really hard. What's the antiderivative of secant cubed of x dx? All right, hint. This uses integration by parts. This uses some swingy, whoosh, action, right? And it's really hard. Good luck, my friends. I'll talk to Mr. Schwartz and see if this is something that we want to do in class together. It is riveting. All right, but with that said, I think I'm going to stop here. That's some integration by parts, lots of examples, and each example kind of exemplified, as examples do. They exemplify something different. So let me just like swing back to the first page. All right, we talked about the integration technique unit. Why do we do it? Please try to find some intrinsic value in the cool puzzles that we will be solving for the next several weeks. All right. We talked about some basic integration techniques. All right, use power rule, some basic stuff that you already should know, just things that you should have technically memorized, but understand why they are what they are. That is what analysis 1A was for. All right, and if I proceed, that we just did an integration practice that didn't involve IBP, but then we got to integration by parts. All right, it is just the product rule. Earlier I said the chain rule. I meant the product rule. It's just the product rule being exploited. Then we did some examples. We did first of all we really emphasized writing down and doing these problems in a consistent way, right? UdV duv. Right? Write it down this way. I guarantee you it'll make the problems easier. Right? You don't want to have to get tripped up by writing down the wrong integral. Right? Write this chart, make it easy on yourself. Right? We did a simple problem, x sine x. Right? We did this one. Right? It required us to do it twice. Right? That's going to happen sometime. Right? Just real quick, let me just remind you that always try to do the problems in the simplest way. Right? Maybe you don't need to use integration by parts. When we did this one, this was just a use sub problem. Right? I tried to deceive you. Hopefully I didn't catch you, but if I did, that's okay. Learn from the mistake. Right? Sometimes you have to really think about what your dv is going to be. Right? In this example, right, you might have intuitively thought that u should have been x cubed and dv been cosine x squared, but the dv needed the x so that you could take the antiderivative of it. Right? Sometimes you're not going to know that you can use integration by parts, but you can. All right, and by making your dv here dx, we were able to take the antiderivative arctan, which is some nasty stuff down here. And then we had some swingy whoosh action. All right, sometimes if you use integration by parts, you're going to never deteriorate one of your functions to 1 or to 0, and then you're not going to be able to solve it. Wrong. You can. If your function will eventually get back to where it was, you can treat the function itself as a variable, move it to the other side, and solve. Which is what we did here with some swingy action. Right? And then, I mean, maybe you tried to do this problem right here. All right, but if you didn't, that's okay. We'll probably look at it in class. But if you attempted it and you solved it, you're an integration by parts expert, and I applaud you. All right. But there you have it. That is integration by parts. That is our first of many new integration techniques, and they're going to be difficult. Don't get me wrong. But with practice, not just watching me, but with practice in class and just doing problems and trying to figure out which one works. Failing, trying a new technique, trying a new DV or a new U. You're going to become masters. And then you will look at integrals and laugh, ha! In their face about how easy they are, when another person might look at it and pass out. Right? You will be experts in time. I wish you all the best of luck in class. Right? To my students, I'll see you there. To Mr. Schwartz's students, right? I will not get to see you struggle, and that's unfortunate because that is a part of this whole process. Right? Good luck, everyone.